Good morning, students. So, let us continue our discussion of the subject discrete mathematics. This is the syllabus, and today we will be focusing on graph theory from Unit 5, which has the following syllabus contents: graphs, degree, connectivity, path, cycle, isomorphism, Hamiltonian graphs, Euler and planar graphs, graph coloring, chromatic number, trees. So today's focus will be on graphs only. Trees will be covered at a later stage. So I am referring my handwritten notes which I scanned. See here, a graph, let us say, is represented by D. It has A comma R. A will be the nodes, R will be the edges. So this is our graph. Okay. So here in this graph, A, B, C and D are the nodes, while AB, AC, BC, CD are the edges. So you have a path, directed path from A to B, B to C, and C to C. It has a loop. See here, it has a loop. But this path is undirected. A to C and C to D is undirected path. Now, what is A here in our representation nodes? The cross product of nodes will be the edges. For example, A comma B is an edge, A comma C is an edge, B comma C is an edge, C comma C is an edge, and D comma C an edge for this graph. Okay, let us say we have A nodes as ABC and B nodes as 1, 2, 3, for example. Then we can have their combinations, edges as A1, A2, B1, B3, B2, which is this representation. You can see here you have A, B, C, which are the nodes. You have 1, 2, 3, again which are the nodes. Now we want to find their edges. The edges are A1, A2, B1, B2 and C3 in this small graph you can see the example of a self loop. You can see here B is a node which has a self loop. For this graph having these nodes A, B, C and 1, 2, 3, if you want to find the out degree of the nodes, for example out degree of A, you have to just find out the outgoing edges of A, and the outgoing edges of A here are 2. So the out degree of A will be 2. Similarly, the out degree of B will be 3, and there is no out degree for C. The in degree for one node say is 2. The in degree for 2 is 2. The in degree for 3 is 1. Suppose you have this kind of statement. Okay. You have A and there is a relationship between A and B. The condition is if and only if B is equal to A plus 3. So here let us say this is my A, so B will be 3. Let us say this is my A, so B will be 4. Let us say this is my A, so B will be 5, like that. You can see here this is my graph. How many nodes are there in this graph? A, B, C and D. So 4 nodes are there. And is there any loop in this graph? Yes, there is a loop in this graph. This B has a self loop. Similarly, how many edges I am saying? 1, 2, 3, 4, 5. Okay, even this loop part. If you see the directed path being given is A to C, C to B, A to C, C to B, B to A, and again B to C. This is the example of directed path. And this is the example of undirected path. Let us explore this. A to C, C to B, B to A to C, and C to D. This because this arrow is not in the same path, directed path. What is a simple path? In a simple path, the node appears only once. For example, this path, take this path, ACB, ACB. So all the nodes A and C and B are appearing only once. Okay. What is a circuit or what is a directed cycle? The circuit or a directed cycle is when you start and end with the same node. Say for example this path ACBA, ACBA. So what is the starting node? A. What is the ending node? A. So a starting and ending with the same node. So that will be the circuit or the directed cycle. There is one more part to be explored, ACBBA. A to C, C to B, B self loop, again A. So again we are starting with A and ending with A. So this also is a circuit or a directed cycle. Now what is the utility of graphs? So graphs are useful for representing data structures. Let us take our same graph here and try to represent a adjacency matrix for the graph. So how many nodes are there? A, B, C, D. So I am taking 4 columns A, B, C, D, and I am taking 4 rows A, B, C, D. Now let us check. Let us check here. We are trying to construct this matrix using this graph. Okay. So A to A. Is there anything outgoing from A to A? No. So put a 0. A to B. There is no path from A to B. So put a 0. A to C. Yes. You have a path. So I am putting a 1. So there is a, again A to D. There is a path. So I am putting a 1. Similarly, let us take B. So B to A will be 1 and B to B will also be 1, rest will be zeros. Similarly, take the case of C. C to B will be 1, C to B will be 1, rest will be zeros. Take D. D to C will be 1, so D to C is 1, rest will be zeros. So just if you look at the graph, you know how many number of edges are there. 1, 2, 3, 4, 5 and this self loop also. So how many edges are there in this graph? In this graph total edges are 6. As the total edges are 6, you can see the adjacency matrix representation also. If you count the number of ones here, 1, 2, 3, 4, 5, 6. So the total number of ones are also 6. The total number of ones are also 6. We are saying graphs are useful to represent data structures. Say for example our data structure is a linked list. What is a linked list? The linked list is a node consisting of 2 parts. One will be the data part, the other will be the address part. So how many nodes are there? A, B, C, D. Okay. So these nodes, let us say how they will be linking. So you have this ordered pairs A to C, A to D. So A to C, A to D. Then B to A, B to B. So B to A, B to B. Then C to B, then C to B, then D to C. So as you can see here, A to C there is no link, and similarly A to D there is a link. Similarly B to A there is a link and B to B there is a link. So from C to B there should be a link and D to C there should be a link. Like this you can represent. So this is my graph. Again you can see this graph. Okay. So what is A? A indicates the nodes. Okay. What are my nodes? Vertices A, B, C, D. So these are my 4 vertices. So let us say A prime is there, and A prime is we can say belongs to A, which has ABD. So it doesn't have C. It doesn't have C. So it is having ABD, this part, ABD. So this ABD, so this is a G prime. This G prime is a subgraph. This G prime is a subgraph which is derived from this main graph, which is derived from this main graph. Now, this subgraph is also an induced subgraph. What is the meaning of an induced subgraph? The meaning of an induced subgraph is that look at this graph, and from this graph you have derived this subgraph. Okay. So which vertex you have removed? You have removed the vertex C. So if you have removed this vertex C, check whether the edges which belong to vertex C are present. No, CD is not there, BC is not there, CB is not there. So they are all removed. So edges related to this vertex which is removed, if they are also removed, then this will be called as an induced subgraph. This will be called as an induced subgraph. So what is this now? From this subgraph we are deriving another subgraph which is its subset. So this is a partial subgraph. Here this is an example of an empty subgraph. So you don't have any, this is rather an empty graph. So there is no connectivity at all, empty graph. Here this is an example of a complete digraph. This also is an example of complete digraph. What you are seeing in complete digraph? Suppose A and B are two nodes. So the edges are bidirectional. So from A to B there is an edge, from B to A there is an edge. Similarly, we are speaking about this graph also as a complete digraph. How many nodes are there? A, B, C. So for each node there is an incoming and outgoing edge. There is an incoming and outgoing edge. So this is the meaning of a complete digraph. Let us try to understand what is a strongly connected graph. What is the meaning of a strongly connected graph? From every vertex there is a directed path to every vertex. For example, A to B, B to C, C to A, like this. So this is a strongly connected graph. What is just a connected graph? It has a path, maybe a directed path, maybe an undirected path, from every vertex to every other vertex. Say for example this. Okay. This is the example of a disconnected graph. This is a small subgraph, this is a small subgraph. There is no connectivity between them. They are not connected with each other. So this is the example of a disconnected graph. Let us move further. Okay. I am referring here a word called as pendant. Okay. But before that we are also referring a word called as degree of a vertex. What is the degree of a vertex? The degree of a vertex is you have to count the number of edges. What is a vertex in this graph? A is a vertex, B is a vertex, C is a vertex, D is a vertex, E is a vertex. So the nodes are called as the vertices. The nodes are called as the vertices. How to find the degree of a vertex? Count the number of edges. Count the number of edges. Say for example, for B vertex, how many edges are there? 2. So the degree of B will be 2. For C, degree will be 2. For D, degree will be 2. For A, the degree will be 3 actually. So for E, what will be the degree? For E, the degree will be 1. So whichever vertex is having the degree 1, E is called as a pendant. E is called as a pendant. Okay. So there is a relationship between the degree of vertices and number of edges, and there is a formula for that. Okay. So summation of degree of vertices of all the vertices of a graph, if you take, it will be equal to 2 multiplied by number of edges. It will be equal to 2 multiplied by number of edges. Let us take this example. Say for example this with respect to this formula. How many nodes are there? 1, 2, 3, 4. 4 nodes are there. How many edges are there? 1, 2, 3, 4, 5, 6. So 6 edges are there for this graph. So what this formula says? Multiply 2 with 6. So 2 into E, 2 into 6 will be 12. It will be 12. So now as the number of edges are 6, multiplied by 2 you get 12. So now what the formula says? the degree of all the vertices, if you add them, summation of, if you take, it should be equal to this 2e, which should be equal to 12. So let us take each vertex and its degree. For example, D, the vertex is D, and the degree is 3. A vertex degree is 3, B vertex degree is 3, C vertex degree is 3. So there are 4 vertices. For each of them the degree is 3. So I am multiplying 4 by 3. So that is coming to 12. So left side is 12, right side is 12. So what it is? This formula is being proved. That what is this formula? Summation of degree of all the vertices is equal to 2 multiplied by number of edges. Now the same undirected, this is an undirected graph, okay. The same undirected graph, you have already seen this, how it can be represented in a matrix form. Take the nodes as column headers and row headers A, B, C, D, and just check here. A to A there is nothing, so A to B, A to C, A to D, 1, 1, 1. So B to A, B to C, B to D, 1, 1, 1. So like this you have to represent. This is the representation. So there is a word here called as Honigberg bridge problem. Now give me a second to represent this it is Königsberg bridge problem. What it is saying is, this Königsberg bridge problem is, let us say this is my Königsberg bridge problem. So you can see here there is a water, everything, and these are the bridges. These are the bridges and these are the land masses. These are the land masses. So the question being asked is, or the problem being posed is it possible to cross each of the bridge? This is a bridge, this is a bridge, this is a bridge. Okay, how many bridges are there? 1, 2, 3, 4, 5, 6, 7. There are 7 bridges. So is it possible to cross each of the bridge only once and come back to the starting point? Let us say we are starting from here. So can I traverse like this only once and come back here? Okay. So this actually is proven by Euler using contradiction. What he gave is, he gave a formula called as F plus V is equal to E plus 2. F plus V is equal to E plus 2 means face plus vertex is equal to H plus 2. As it is not possible here, through contradiction it is being proved that it is not possible to solve this problem. Similarly, there is one more problem called as 4 utilities problem or utilities problem or 3 utilities problem. So say for example, how this utilities problem is being represented, number of houses, let us say number of houses are 3 and the utilities are gas, water and electricity. Now we have to give connection to each house, all of them. So gas line, water line, electricity line, in such a way that there should not be any interconnection. So there should not be any interconnection. So that also is proven using the same formula, F plus V is equal to E plus 2. So there is one more term being referred here called as isomorphic graphs. So in an isomorphic graph, what is there? Equal number of edges, equal number of vertices, equal degrees. Say for example, you have vertex 1, 2, 3. You can take any example wherein you can check whether both the graphs are having the same number of vertices, same number of edges, same degree. Such graphs will be called as the isomorphic graphs. You have Google Maps. Google Maps will be using shortest paths, and Google Maps are what? They are nothing but graphs. They are nothing but graphs. So you can see here the example of isomorphic graph. This graph and this graph, they are congruent, they are similar in structure, there is one-to-one mapping, they have vertices which preserve incidence relationships. So such graphs are called as isomorphic graph. Even these two graphs, this graph and this graph, if you count the number of vertices, number of edges, all the vertices similar vertices of these two graphs will be having similar degrees. So these are few of the examples wherein you have isomorphic graphs. Even these two graphs are isomorphic. Here E is the pendant and V phi is the pendant. In the last one, if you see these two graphs, we are claiming that these two graphs are not isomorphic because there are two pendants here, 5 and 6, and there is only one pendant here, F. So what is a Euler graph? In a Euler graph, there is a walk, and that walk contains all the edges of the graph. So such a walk is called as a Euler line, and such a graph is called as a Euler graph. So we have seen what is a subgraph already. For example, ABD is a subgraph which is represented by G prime. This also is a subgraph. So if there are no edges in common, such subgraphs are called as edge disjoint subgraphs. So if there are no vertex in common, then vertex disjoint subgraphs. What is a walk basically? There is an alternate sequence of V and E, vertex and edges. Begin and end. You will be beginning with a vertex and ending with a vertex. In a walk, no edge appears more than once. A vertex may appear more than once. Say for example, where is my graph here? Okay, this is my graph. Okay, you have a walk here, V1B, V2E, V3H, this is a loop, then V3D, then V4. This is a walk where V3 is repeated, you can check. Similarly, in this walk also, V4C, V2F, V5G, V6, you have a walk. So similarly, if there is a closed walk, in a closed walk it begins and ends with the same vertex. For example, it has begun with V1 and it has ended with V1, V1B, V2C, V4A, V1. What is a closed walk? In a closed walk, all vertices are of even degree. All vertices are of even degree. What is a Euler circuit? If and if the degree of every vertex is 2. What is a Euler path? If and if there are at most 2 vertices with odd degree. This is Dijkstra's algorithm. A very simple example to find the shortest path. Even Google Maps, these kind of applications also make use of this Dijkstra's algorithm. This is my graph, okay, and 1, 2, 3, 4, 5, these are my nodes, while these are my edges. These are my edges, and there are weights given to these edges. So what I will be doing is, I will be just to apply Dijkstra's algorithm, I will be putting this nodes as column headers, and initially all the distances we are calculating as infinite distance. Now we will be starting with 1. Where is 1? 1 is here. We will be starting with 1. So 1 distance from 1 to 1 itself is 0. 1 to 2, well, how much is the distance? 4. Rest I will be keeping it as infinity. 3 is not directly reachable. Okay. 4 is directly reachable, but the distance is 8. While 5 is not directly, so I am keeping it as infinity. So in this traversal, I know that 1 to 2 is the smallest, so the minimum value I am taking is 4, and this is happening through node 2. So I have taken 1 comma 2 this path now. Now this 1 comma 2, from 1 comma 2 I will be reaching to 3 with a cost of 7, with a distance of 7, okay, and to 5 I will be reaching with a distance of 18. So here in this, after 4 the next minimum will be 7. So the node number is 3. After that the node number is 4, and after that the node number is 5. So like that we will be calculating the shortest path 0, 4, 7, 8, 15. This is the Dijkstra's algorithm. For this graph also, having these nodes A, B, C, D, E, F, G, H and the weights given, you can try out the shortest path using Dijkstra's algorithm. In this slide what we are seeing here, say for example we will take simpler things. This is a graph, right? Which are the nodes in this graph or vertices in this graph? V1, V2, V3, V4. Let us take the degree of each one of them. What is the degree of V1? 2. What is the degree of V2? Degree of V2 actually should be 3. What is the degree of V3? The degree of V3 is 1. What is the degree of V4? The degree of V4 is 2. What is the degree of V5? There is V5. V5 is disconnected, so there is no degree. So this one. So degree of V1 is, I am speaking about this graph now. This is a multi-graph. This is the example of multi-graph. What is a multi-graph? Multi-graph has multiple edges. You can see here V1 to V2. If you have two nodes, there are multiple edges from V1 to V2. This one and this one and this one. So if you take the degree of V1 now, degree of V1 is 3 here. Degree of V2, actually it should be more. Degree of V3 is 1 and degree of V4 is 1. Let us try to understand the next term, which is a pseudo graph. What is a pseudo graph? It has loops like this. V3 has a loop and it has multiple edges. V2 also has loop. It has multiple edges. Now say for example, if I want to find the degree of V2, what should be the degree of V2? 1 plus 1, 2 plus this you have to add, make it 2 as it is a loop. That's why it is becoming 4. Similarly, degree of V3, 1 plus 2, that is becoming 3. If you remember this formula, 2 multiplied by number of edges actually will be equal to how much? The degree of all vertices added together. This is called as a handshaking lemma. What is the degree of the graph then? It will be with the largest vertex degree. Whatever the largest vertex degree is there, that. Suppose you have 6 vertices and these are the degrees. So summation of all those degrees will be odd. So we cannot construct graph for such a graph, for such an entity. Again, if you look at this graph, what you are looking at this graph, in this graph you have nodes such as V1, V2, V3, V4, V5. So if you look at all the vertices, what will be the degrees? Degree of V1 is 2, V2 is 2, V3 is 2, V4 is 2, V5 is 2. So it means for all the vertices the degree is 2 only, the degree is same. So in a regular graph, degree is same. So which graph will be called as a regular graph then? The graph having same degree. Even here the degree is same, even here the degree is same. Suppose there is a regular graph with degree k, then such regular graph will be called as a k regular graph. So 0 regular graph, 1 regular graph, like that. Coming to simple graphs, so maximum number of edges possible with n vertices for a simple graph is this NC2, okay, combination, which is n into n minus 1 by 2. Say for example here, what is the value of n here? N is number of vertices, so 3. So it is coming to 3 edges. How many maximum number of simple graphs are possible? 2 to the power of NC2. So that will be 2 to the power of n into n minus 1 by 2, which is coming to 8. So for such graph we will be drawing these 8 subgraphs. This is one subgraph, this is one subgraph, this is one subgraph, this is one subgraph. Here you are seeing the example of a parallel edge. So which are the parallel edges? E1 and E2 are the parallel edges, because E1 is equal to how much? V1 V2. E2 is equal to how much? V1 V2. Even here also in this graph, E7 and E6 are parallel edges. Both of them are represented for what? V1 V4. Now we are referring a word called as bipartite graph. Okay. So what is a bipartite graph? So bipartite graph does not have odd cycle. Bipartite graphs are symmetric. Bipartite graphs are two colorable. Bipartite graphs are having set of vertices which can be partitioned into two disjoint sets. Let us say this is my graph and I am calling this graph as a bipartite graph. Why I am calling this graph a bipartite graph? Because I have divided this graph into two disjoint sets. On the left side there is a set, on the right side there is a set of vertices, and so here the edges will be connecting a vertex in one set to the vertex in another set, but no two vertices of the same set will be connecting with each other. So this is the example of that. Even this is the example of that. Say for example this graph. In this graph there is a very interesting aspect called as two colorable. A bipartite graph have the property of two colorable. Suppose I want to check whether this graph is a bipartite graph or not. Just start coloring them. So how I am going to color? No two adjacent nodes will be having the same color. I started with this say blue. So its adjacent is red, its adjacent is red, its adjacent is red, its adjacent is red. But now this is not following the property. It is both adjacent are having the same color. Hence I am proving that this is not a bipartite graph. We have Google Maps. What is a Google map? You can call it as a big giant graph of the world, where vertices is equal to location of places, edges is equal to distance or time. You can find shortest route using Dijkstra's algorithm or some other method. There is one more application called as gaming trees. Game tree will be used for analyzing games like chess, checkers, tic-tac-toe. They are useful to develop game playing strategies. Here in game trees, vertices will be position in the game, edges will be the legal moves, path will be the sequence of moves, route will be the starting point. Okay. So let us say we have even level vertex. So starting first player move, odd level vertex you can represent it as circle, even wala you can represent it as a box. This is a second player move, and leaves will be the final position. Terminal vertex, if it is circle 1, first player has 1. If it is box -1, second player 1, like this. Let us come to today's discussion's last point, Hamiltonian path. So here we have to visit every vertex only once. So Hamiltonian is actually difficult. It is an NP complete problem. So I have seen already this. You can see here Hamiltonian circuit. Okay, A1 B2 D5 C6A, A1 B2 D5 C6A. So A4 D2 B3 C6A, A1 B3 C5 D4A. These are all the example of Hamiltonian. What is a Hamiltonian path? Here the path will be crossing every vertex only once. Okay, for example this path AI HB CD EF G, ABI HC DG FE. What is a Hamiltonian circuit? The path which will be starting and end at the same node, say for example. This is starting at W, ending at W, starting at W, ending at W for this graph. This is the example of a complete graph. What is the example of complete graph? What is the meaning of that? Every vertex is connected to every other vertex. A, take any vertex, C, it is connected to all the other vertices. Hamiltonian circuit is not there when in a graph having a vertex of degree 1, all edges of vertices of degree 2 must be there in the circuit. So with this we are stopping this discussion.